Have you ever wondered how consistent performance of components in an integrated circuit is ensured? Well, in the realm of analog layout, a key player in this process is something known as matching. Matching is absolutely crucial to ensuring that components, like transistors, perform consistently within an integrated circuit. You see, in the world of electronics, even the smallest inconsistencies can potentially lead to significant performance variations, which, needless to say, can be quite problematic. Therefore, achieving matching in an analog layout is not just a nice to have, it's a must-have. So, how do we go about achieving this matching? Well, there are several key steps involved, each carrying its own level of importance and each contributing to the overall goal of consistent component performance. Today, we will explore the key steps for achieving matching in analog layout. So, buckle up and let's dive deep into the fascinating world of analog layout matching. Firstly, we must consider layout symmetry. In the world of analog layout, symmetry isn't just about aesthetics, it's a vital strategy for minimizing variations. When matched components are placed symmetrically, they are more likely to operate under similar conditions. This similarity in operation can lead to consistent performance across your integrated circuit. But symmetry isn't the only game in town. We also need to pay attention to the common-centroid arrangement. Imagine a geometric centroid, the central point that balances a shape. Now apply that concept to your matched components. By arranging these components in a common-centroid configuration, we can further reduce layout-dependent variations. Here's how it works. You interleave the transistors of a matched pair. This interleaving acts like a buffer, helping to decrease variations that could otherwise affect your circuit's performance. That's the beauty of common-centroid arrangement. It's about maximizing harmony in your layout. Thus, layout symmetry and common-centroid arrangement are crucial steps in achieving matching. Moving on, we come to matching lengths and equal loading. In the realm of analog layout, it's crucial to ensure that the lengths of critical interconnects, such as transistor channels, are identical for matched components. This is because it minimizes the variations caused by parasitic capacitance and resistance, which can affect the overall performance of the circuit. Now, let's talk about equal loading. By matching the loads connected to the devices, we maintain symmetry, which in turn helps in achieving similar response characteristics. This is a vital step in ensuring the consistent performance of the components. Lastly, we have the use of dummy devices. These non-functional elements are integrated into the layout to balance it and improve matching. You see, dummy devices play a key role in compensating for variations in process and environmental conditions, which can be a game changer in achieving the desired performance. These techniques help further reduce variations and enhance the consistency of component performance. Next, we must account for corner effects and electromigration. In the world of analog layout, corners aren't just points where two lines meet. They can be regions of different environmental conditions that can impact the matching of components. To mitigate this, matched components should be placed away from the corners of the chip. Another critical consideration is electromigration. This is the gradual movement of ions in a conductor, which can cause variations in device characteristics over time. This is especially important in long interconnects. So how can we ensure a uniform substrate bias and reduce variations? Enter local well tap sharing. By sharing well taps locally between matched devices, we can maintain a consistent substrate bias. This method is like a symphony conductor, ensuring all parts of the orchestra, or in our case, the circuit, work together harmoniously. These considerations ensure that our layout remains robust against various environmental and process conditions. Finally, we come to layout verification and statistical simulations. After meticulously arranging our components, we need to verify our efforts. This is where layout verification tools like Calibre come into play. Calibre checks our layout for adherence to design rules, ensuring that our layout meets foundry-specific standards and guarantees manufacturability. It's like having a second pair of eyes, catching any potential issues before they become real problems. But we're not done yet. Remember, manufacturing processes are subject to statistical variations. To account for these, we introduce Monte Carlo simulations. These simulations provide a range of possible outcomes based on random variations, giving us an understanding of how these variations can impact our circuit's performance. By identifying and mitigating the impact of these process variations, we can enhance the matching and performance of our components. With these steps, we can effectively ensure consistent performance of components in our integrated circuit.